We're now going to go over the mean value theorem for integrals. As we'll see, the mean value theorem is important because we use it to prove the second fundamental theorem of calculus, among other applications. And the second fundamental theorem of calculus is in itself a very important result. So that justifies our study of the mean value theorem. So the mean value theorem makes this statement. If we start with a continuous function f of x over some interval a, b, then there exists a number c somewhere in the interval a, b in which the definite integral from a to b of f of x dx is equal to f of c times b minus a. Now graphically what this theorem is telling us is illustrated down here. So here we have the graph of some function y equals f of x, and the same graph over here. Now in this case, since our function is positive, the definite integral is giving us the area of this shaded region right here between a and b, bounded above by the function f and below by the x-axis. That's what the definite integral is giving us, the area of this shaded region. Now the mean value theorem makes a statement that there is some number c, if we look at this graph over here, there is some number c between a and b in which f of c, which is this number on the y-axis, if we go up to the graph and over, that's the number on the y-axis, f of c times b minus a gives you back the same area. Now think of it like this. This quantity here, f of c times b minus a, is representing the area of this rectangle, because b minus a is this distance, that's b minus a, and f of c is simply this height right here of the rectangle, that's f of c. So the area of this rectangle, as it is shaded here, is just f of c times b minus a. So that's what the mean value theorem is telling us, that there exists this number c in which f of c times b minus a, which is the area of this rectangle, is the same as the definite integral from a to b of f of x dx. Now the way you can think of this in a physical sense, here's how I think of it. I like to think of this as being like a thin film of water. Suppose we have two glass sheets here and we have water in between the glass sheets, and the water is bounded by these lines, and then it's bounded by the curve right here, f of x. So suppose this is water in here, and we have it bounded by a side wall here, a side wall here, the x-axis down here, and then our function is some type of membrane that's holding back the water. And then what we do is we remove the membrane. We just get rid of this bounding membrane defined by the function. Well, the water will slosh down to an average level. It will slosh down to exactly this level right here. And so what you can think of this number f of c as being, you can think of it as being the average value of the function from a to b. That's really what it's representing. And that's exactly what we'll define in a second. Now, the proof of the mean value theorem is not that difficult, so let's take a quick look at it. The proof is very graphical in nature, so now if our function f of x is continuous, then it will take on both its minimum and maximum value over the interval from a to b. So let's let little m be the location where f of x has its absolute minimum, and let's let capital M be the location between a and b where f of x takes on its absolute maximum. Now consider the graphs that we have down here. If we look at f of little m times b minus a, that will give us the area of this shaded region. Okay, so this height right here that's f of little m, and this distance is b minus a, so we get the area of this rectangle. On the other hand, the definite integral is giving us the area of this shaded region. And then if we look at f of capital M times b minus a, well, this distance is f of capital M. That's where f has its maximum value. This is where f has its maximum value, and this number is the maximum value on the y-axis. So if we consider f of m times b minus a, which is this distance, we're going to get the area of this shaded region. Well, notice then the area of this region is right here. That's less than or equal to the area of this shaded region, which is our definite integral, and that's less than or equal to the area of this shaded region, which is f of capital M times b minus a. Now what we do is we just divide each of these terms in this inequality by b minus a. And what you end up with is this. So we end up with a statement that the minimum value of the function over the interval from a to b is less than or equal to 1 over b minus a times the definite integral. And this is less than or equal to the maximum value of the function over the interval. So then, we have, by the intermediate value theorem, that there must be a number c between a and b in which f of c takes on that value. You see, this number is between the minimum value of f on the interval and the maximum value of f. So since f is continuous, there must be a number c between a and b in which f of c equals that number. That is a statement of the intermediate value theorem. And this, if we just take the b minus a, multiply it over with the f of c, we end up with our statement of the mean value theorem for integrals right there. And so that proves our result. Now let's take a look at a few examples. Before we look at an example, we need one definition first, and that is the average value of a function. And we've actually already seen this when we proved the mean value theorem. So our definition goes like this. If f of x is a continuous function on the interval from a to b, then we define the average value of f over the interval from a to b to be this quantity. In other words, this is just our f of c that is referred to in the mean value theorem. So that's what our average value of the function over the interval from a to b is defined to be. Now let's take a look at an example. So let's find the average value of this function over the interval from 1 to 4, and then let's interpret our answer graphically. So, well, all we have to do is evaluate this. Our average value it's simply going to be 1 over b minus a Now we just need to evaluate this definite integral. So this will be 1 over 4 minus 1 is 1/3 times, now the antiderivative of 3x squared, that's just going to be x cubed. Antiderivative of 2x is just x squared. Notice if we differentiate this, we get back 3x squared minus 2x. And then we just have to evaluate this from 1 to 4. And so this is equal to and that equals 16. So that's the average value of this function over the interval from 1 to 4. And graphically, what we see down here we have the graph of our function, 3x squared minus 2x. and over here as well. So the shaded area here, that represents our definite integral from 1 to 4 of 3x squared. So this represents this area down here because our graph is positive. And so what we're saying then is that this value right here, 16 on the y-axis right there, that's our average value for our function. And so if we were to evaluate the area of this shaded region, which is 3, this width is 3, and we multiplied by 16, so 3 times 16 is the area of this rectangular region, that is actually equal to the area of this shaded region. And so we call 16, this height, our average value for the function. Let's try another problem. So let's find the average value of the sine function over the interval from 0 to 2 pi and interpret our result. Alright, so the average value, that will be 1 over 2 pi minus 0 times the integral from 0 to 2 pi. And that is equal to and we can simplify that as once again, notice the antiderivative of sine is negative cosine, and then I just combine the negative with this 1 right here. So negative 1 over 2 pi times cosine evaluated from 0 to 2 pi, and we end up with now recall, cosine of 2 pi, that quantity is 1. This is 1 right here. And the cosine of 0 is also 1. So we end up with 1 minus 1, which of course is 0. So we end up with our average value being negative 1 over 2 pi times 0. And so this is just 0. So our average value comes out to be 0. Now if we look at this graphically, this makes sense. Because down here we have the graph of our sine function. And so you notice when you evaluate the integral from 0 to 2 pi of the sine function, this quantity is giving you the sum of the signed areas. And so this area here is the same as this area down here, but when you evaluate this, this is giving you A1 minus A2, which we can see is just 0. So you can think of this area here as being canceled out by this area down here, and so the average value of the sine is 0. It makes sense that its average value should be 0 because this area is canceled out by that area. And so that's our average value of the sine function over the interval from 0 to 2 pi. And so that concludes our introduction to the mean value theorem.